Let us continue what we were talking about last time, which was on this thing we called motional EMF. And we were looking at this example where we had two metal rails connected to each other by a resistor. And there was a metal bar here, and we were moving the metal bar in the presence of a magnetic field. So once again, this is one of these situations where you have a magnetic field that's applied by something else. Okay, if there's going to be a current in here, yes, it'll create its own magnetic field, just as the wire in the problem we just did create a magnetic field in the presence of the electron. But there's something else here. Maybe it's a coil that we're not showing, or maybe it's a bar magnet or something, creating a magnetic field that's pointing out of the board, let's say. So that is B. And the bar we are moving, or it's moving to the right with some speed. So let us, now we did this question last time, but let's just ask it again. So the magnetic field is pointing out, the bar is moving to the right. What's the direction of the conventional current in this case? See if we can determine what we had. See if you can remember what you had to do, if you need to look back at your notes from last time. Okay, evenly split. So very few remember what we did last time. So let's do it. Let's try it again then, which is fine. No, that's fine. That's fine. I wasn't sure what was going to be the result here. Okay, what do we say about, let's just look at the bar at first. When we say it's moving through the presence of a magnetic field, right? And so the idea is we looked at the mobile charges inside the bar. They're all moving in the same direction as the bar is, right? So if we think about a single electron in the mobile electron C, what's going to happen to it as it moves to the right? Up, force is QV cross B, right? So V cross B is down, but multiplied by negative charge, force is up. Okay. So there's a magnetic force. In fact, let's draw that in a different color. Let's make it green, maybe. Okay, magnetic force is up. So what happens to the bar? It polarizes. So how do I draw the polarization? Minus and plus. Okay, minus up here, plus down the bottom. Okay. All right, so you've got this polarized bar, which if it is polarized, it's creating an electric field, right? Which is pointing up. And therefore, there'd be an electric force on the electrons, pointing down. And I'm starting to squeeze lots of things into this bar here, so let me try to redraw it. That's the electric force, and the electric field is up. Okay. So which way are the electrons going to move? And this really is the question here. And how do we think about this? Well, it's easy to say, well, the electric force is down, so electrons are going to move down, current's going to move up. But if you think about the analogy with a circuit, just have a single resistor, and here's a battery, for example, then, well, if this side is polarized, we have a similar situation where we have a polarization of positive charges on the bottom, negative charges on the top. So that looks like the plus terminal of the battery. That's the minus terminal of the battery. And the conventional current in this case flows clockwise, right? So I is going that way, capital I. And so we got to have the similar sort of thing here. We have a polarization here driving the current through the rest of the circuit. If you were to draw the electric field in the rest of the circuit, you'd have electric field pointing away from the positive terminal up through this resistor. And it's probably going to be a larger electric field through the resistor. and towards the negative terminal. And so, in fact, the conventional current will flow that way. Okay, little I would go the other direction. Okay? Does this make sense? Okay, so much like in a battery, and in the battery we have, again, the same sort of thing. Negative charge here. There is an electric field inside the battery which is pointing upward. There is an electric force downward. But that electric force inside the battery is not what's driving the current, right? There has to be a non-electric force or a non-Coulomb force in the battery that is driving the current the way it doesn't want to go in some sense, right? The opposite direction. So that the electrons will actually travel in that direction. Little I, again, will be in the opposite direction of capital I. So at that point, once it's in the rest of the wire, it's the electric force that does drive the current. So the electrons in here flow in this direction because there's an electric force in the opposite direction. But in here we have this sort of balancing between the magnetic force, which is what's initially causing the polarization, and this electric force in the opposite direction. So in this case, it's the magnetic force that's playing the role of the non-Coulomb force that's driving the current. Okay, remember that the work done by that non-Coulomb force per unit charge is defined to be the EMF. Okay, it has the same units as volts, potential difference. So in this case, this is called motional EMF because the movement of this bar through the magnetic field is creating a magnetic force that's driving the current. Okay, so it's essentially this magnetic force is playing the same role as the non-Coulomb force. We could calculate it. We could figure out how much this potential difference is because we can say that the potential, the EMF, in an ideal situation, if it's a very low resistance bar, the EMF is going to be the same as the potential difference across this bar. Okay? And the magnitude of that thing is just the electric field times the length. So let's give this bar a length. Let's say the length of it is capital L. So that's E times L. How am I going to find E? How would I find the electric field? Where would I start? Yeah. Okay, so what's canceling out? Yeah, okay, so QVB sine theta and Q times E, right? The electric force and the magnetic force, we have once again a situation where if the charges are moving at a constant rate, okay, we've reached a point where the forces are balanced. Okay, the net force is 0, approximately. Magnetic force is equal to the electric force. So once again, like the Hall effect, we're starting here with essentially the momentum principle, or the fact that the charge, the acceleration is 0. Net force is equal to 0, therefore QVB is equal to Q times E. Q's cancel. We can plug that electric field into here, and we find that the EMF is going to be V times B times L. Okay, so we can calculate this. We knew how fast if we knew the dimensions, right? How fast the object's moving, magnetic field, and the length of the bar. Let me ask a seemingly unrelated question at first, and then we'll come back to this circuit in just a second. Here's something we haven't talked about in a while, but we did a demo on it. If you have a current running through the presence of a magnetic field, and once again, this magnetic field is not due to the wire, it's due to something else, and we're just running a current through this externally applied magnetic field. We saw that there's a force on the wire. What direction is the force on the wire in this case? Okay, so we have, most of us, just barely remember this, we have a current in the presence of a magnetic force, and you can just, well, first of all, you get the direction. We can just think of this as mobile charges moving. Okay, if they were positive charges or negative, doesn't matter. If you have conventional current, think about the flow of positive charge. Positive charge is moving to the right, cross with a B into the page, thumb points up, right? So we have a positive y direction. And this, and you could do negative charges as well, but this comes from, remember we had also worked out another version of the magnetic force, which was I delta L cross B. Look familiar? Yes? No? Sort of? Okay. So there are magnetic forces on moving charges, and therefore there's magnetic forces on currents in a wire. Well, we've got a current in this circuit now. We said the conventional current was clockwise. Is there a magnetic force on the entire bar as a current runs through this bar, and it's drawn here, moving down through the bar? If so, what's the direction? Okay, this is always a question that causes some problems, although most of us are saying that there's got to be, or not just barely, actually a little less than a majority of us are saying that there's got to be a force to the left. Okay, because that is the force that's essentially due to the current. Okay, we've already established that there is a current, conventional current flowing clockwise, and so if you just look at the motion of the current, let's redraw this just to make the diagram a bit more clear. There's a current in this bar going down, and it's in the presence of a magnetic field everywhere in this region that is pointing out. And so, just from I delta L cross B, that's I, that's B. We get a force that is I cross B, thumb points in that direction. Now, didn't we just say that the magnetic force is upward on these charges? A lot of people answered that. Well, you got to be a little bit careful, okay? It's sort of thinking about the choice of system and what happens initially and then what happens once you have a current flowing. You think about initially the charges aren't moving, then you just start to move this bar, and if you're focusing on a single charge, there's going to be a force upward. But if you're focusing on the overall bar and looking at the current through it, then we're focusing on the force on that current and looking at this version of the magnetic force law to get the direction of the magnetic force. Now you can think of this another way, and this might help clear it up a little bit, which is this. Let me draw this bar again. The bar is moving this way, okay? And there are mobile charges in here, presumably electrons, that are moving upward. But the whole bar is also moving that way. So if I were to sort of look at a single electron, how's it really moving? Yeah, kind of up at an angle, right? If I were to sort of, if I could follow an electron as the bar moves to the right, an electron moves up. So the path the electron takes is sort of like that, okay? If you think about that, then the force on that electron, V cross B is that way, but it's really an electron, so it's going to be, the force is going to be that way. You get a force that is, like any other QV cross B force, perpendicular to the velocity. But what we're doing is we're sort of looking at two different components of that force. Okay, I could break this force up into a component along the direction of the bar. That's the force that's causing the current to flow. Okay, And then I could break this force up into another component that's perpendicular to this bar. That's essentially this force. Okay, that's this force. And so we're sort of looking at two different aspects of the same interaction or same phenomenon here. It's just that we're focusing on two different things. One is what's causing the current to be driven in the first place, what's causing the polarization of the bar. And the other is once you have the current flowing, what's going to happen to the bar. Okay, and what is going to happen to the bar? It's moving to the right, but there's a force to the left, so what's going to happen? It'll slow down and come to a stop, won't it? Something. Does that make sense? Well, okay, if it comes to a stop and if there's no velocity, then there's no magnetic force anymore, right? So there's not even going to be any polarization. If it comes to a stop, then there's no V cross B, no polarization, no current's going to flow. What about, let me say the magic word here, what about energy? Needs energy to keep moving. Why? Where's the energy going? Yeah. Exactly. The energy is being dissipated by the resistor, right? We have energy being dissipated by the resistor. So it's got to come from somewhere. Where's it coming from? The kinetic energy of the bar, right? The kinetic energy of the bar. And so energy is being conserved here, right? Because if energy from the kinetic energy of the bar is being converted into heat, right, thermal energy as the resistor dissipates energy, then it can't keep moving forever. It's got to be slowing down, which leads to a force in the opposite direction, which is going to slow it down. Okay. So what do we have if we want to keep a steady current flowing? What do we have to do? We have to add energy, or someone said it. We have to push it. We have to push it in the opposite direction, right? If you want to maintain this thing at a constant speed, you've got to push it at the opposite direction to keep a steady current flowing. Okay. We've talked about, first of all, let's see if we can calculate this force, by the way. We have the current, and let's say the resistor has a resistance of R. So if we know the potential difference, we worked out the potential difference, the EMF, to be equal to V times B times L. So the conventional current is going to be what? What's the potential difference across the resistor? Okay, IR, right? IR. Delta V across the resistor is just I times R. So the conventional current is going to be delta V over R, and that delta V happens to be equal to VBL. Okay. So the current we could work out if we knew the resistance. How would we find the force, namely this force on the bar pointing in the opposite direction of its motion? How would we find that? What do we need to know? The velocity. Okay, we need to know the velocity, but that we've used that to find the current. Okay, and this force depends on the current, so that is going to show up. Oh, the electron velocity. Yeah, the electron velocity, which is essentially that, right? That component of the velocity. That essentially is the drift speed. Okay, we could do that if let's see. If you wanted to do it microscopically, we could do it that way. Okay, but we have a macroscopic property, which is the resistance. So we've already used that to find the conventional current. If you wanted to, we could relate that to Q and a V, where in this case I mean the drift speed. Okay, so you could do that if you wanted to, but we don't know the area, we don't know N, that sort of thing. Okay, so all I'm trying to do is apply essentially this formula, right? And in this case, I have the current, delta L is just the piece or the length vector in the direction of the current. And what length am I talking about? Length of the bar. Okay, so that's just going to be L. The magnetic field I've got, it's uniform. And when I take the cross product, the angle between L and B is what? 90 degrees. Okay, so this is just going to work out to be I delta L B for the magnitude of this force. Or just ILB if I'm just calling this L. And I've got the current, so I can figure out this force as well. I have V times B times L over R times another L times B. So this is V BL. Let's write it up here. The force is going to be V B times L squared over R. Okay? Okay, so that's the force. Now, we said we needed to input energy in this system in order to keep it moving at a constant speed. Let's think about the power. Let's think about the power needed to keep this moving at a constant speed. I have to do work to keep it moving, and I have to apply a force in this direction. And the magnitude of that force, in order to keep it moving at a constant speed, has to be equal to what? Right, the magnetic force in the opposite direction, right? I have to have a net force on this thing of 0 to have a constant speed, right? So that's going to be V B L squared over R, okay? How do I figure out how much work I do on it? What's work? Force over a distance, right? So let's say I move it some distance delta x. And so the work is just going to be F times delta x, right? So I have V BL squared over R times delta x. And then the amount of power I'm inputting into the system is, what's power again? Work over time, work over time. Okay, so power is work over time. So that's this work, V BL quantity squared over R delta x divided by some amount of time, call it delta t. Well, what's that? That's the speed of the bar, right? That's how fast we're moving it. So we're going to get another factor of V here, and this becomes V BL whole quantity squared over R, okay? That's the amount of power I have to input to keep this thing moving at a constant speed. If we're in a steady state, what do I know about the amount of power I'm inputting? It's constant. Where's the energy going again? Resistor, right? The resistor is dissipating the energy. So what do I know about the power output of the resistor? It's constant. And it's got to be equal, right? It's got to be equal to the power input. In the steady state, there's nothing changing. So the amount of energy I'm pumping in has got to be equal to the energy flowing out. Well, let's see if that's true. What did we work out for the power, electric power? Power dissipated by a resistor or power dissipated by an electric element? Anybody remember the formula? There's an R squared in. Okay, what's the more general formula? There is an R squared in it for the resistor, but what's the more general formula? Current times voltage, right? Current times voltage. I times delta V. Delta V across the resistor is, well, it's EMF, that's true, but what's the Ohm's law? IR, right? So we have I squared R. What was the current again we worked out? The current was the EMF divided by the resistance, right? So we have delta V squared over R squared times R. So we're going to a factor of R is going to cancel out. So I have delta V squared over R. And delta V was the EMF. And that EMF we said was VBL, so that's VBL squared over R. And what do we get? Same thing. We get the same thing, which is good. Okay, this works out. The steady state says, again, power input's got to be equal to power output, and calculated two different ways, one by just looking at the work we're doing per unit time, the other by looking at how much energy the resistor is dissipating per unit time, gives us the same result. Okay, what is this thing? It's a generator. It's a generator because we're taking kinetic energy and converting it into electrical energy. It's not a very useful or practical generator, okay? Because you'd have to have two rails that go on forever, right, and keep running this thing forever. So rather than have a bar running on two rails, instead you can make it spin, or make a coil spin inside a magnetic field. And so you can do this instead. Okay, so we have here a few horseshoe magnets creating a magnetic field, and then what I'm cranking is a coil of wire. There's just lots and lots of turns of wire here. It's essentially the same thing. It's a bit more complicated because now instead of forces, you're dealing with torques and so forth, but let's just sort of sketch out what's happening. If you have let's say you have just a square coil of wire in the presence of a magnetic field. Let's say the magnetic field, now I'm kind of drawing this in perspective here, so it's going to be a little bit tough to draw. But this is the axis, and we're going to turn it in this direction. And there's a magnetic field throughout this region. Let's say it's pointing upward. So that's B. Okay. Well, let me draw this edge on because it might be a little bit easier to see what's going on there. So there's one loop of wire that is rotating in this direction in the presence of a magnetic field that is pointing up. And that magnetic field, again, could be made by a bar magnet or what have you. And at this point, we want to focus on sort of this rod, this length here, and this length here. So sort of this segment and this segment, which is moving, that segment's moving that way with some speed, and that segment's moving that way at the same speed. So let's think about, the first step is looking at a single mobile charge and figuring out the direction of the polarization, right? What's going to be the direction of the magnetic force if I have a single mobile charge moving in that direction? Out, right? Out towards us. So what happens on the front of this bar here? Well, okay, again, what was the force? It was a force on what? Imagine a single positive charge. Maybe that's easier to think about. A single positive charge moving in that direction would experience a force outward, right? So what happens to the front of the bar? Polarizes what sign? Positive. What happens to the back? Polarizes negative, okay? What's going to happen down here? It'd be the opposite direction of polarization, right? Because if you imagine, again, for simplicity, just think about a positive charge. V cross B is in, so this would become positive, this would become negative. And then you can make an analogy to a circuit once again and think about sort of two batteries in series, right? Here's the positive terminal, here's the negative terminal connected to a wire to another battery where here's the negative terminal and the back is the positive. It's the same thing. So what's going to happen in here? We're going to have a conventional current flowing in what direction? Well, it's hard to say what the direction is the way I drew it, but if I were to draw the conventional current here, would be coming into or out of the page or the board? Out, right? Because here's the positive terminal. Conventional current is going to flow out of that terminal. I's coming out at the top, and I is going to go in at the bottom. Okay. But now we have a current, and so there's going to be a force that tries to slow the overall motion down. Essentially, there's going to be a torque on this spinning coil, and you can get that from, again, our I delta L cross R force, or cross B force, okay, where I is out, I cross B gives me a force in that direction. I is in here, so I cross B gives me a force in that direction. And notice how this force, this thing is spinning this way, but it's trying to slow it down, right? There's going to be a torque essentially in the opposite direction. So hence I have to keep cranking, or I have to have something else do the cranking for me. What else could do the cranking for me? Wind, okay, an animal, okay, we could have an animal power generator. That's certainly possible. Wind could do it, right, if we connect it to a windmill. What else? Waterfall could do it, yeah. And then you have a perpetual motion machine, right? You can get the generator to power the motor and the motor to power a generator, and you're all set for all your energy needs forever, right? You can get steam, right? You can hook up a turbine and get steam to push this, right? And you can get the steam from boiling water, and your boiling water can be heated by nuclear power or by gas or by solar or by oil or coal or what have you, right? But the idea is that we've got a way to convert mechanical energy into electrical energy. That's what a generator does, okay? So someone said a motor. What's a motor? What do you do with a motor? You convert the electrical energy into kinetic energy, right? So the simplest sort of motor, and we won't go through all the details here because it can get kind of complicated, but it's basically all based on this principle. What if let's make, instead of a simple sliding wire generator, let's make a sliding wire motor. Instead of supplying the kinetic energy to the bar, let me instead hook up a battery. Positive, negative terminal. So I hook this battery up. And again, I still have this magnetic field pointing out. Okay? So the battery is going to drive a conventional current in this direction, right? And so it's the battery that's driving the current, but there's a current in the presence of this bar that's free to slide, and the force is going to be I cross B gives us a force in that direction. Well, okay, I don't want it to move in that direction, so I'm going to flip the direction of the battery. Plus, minus. So I'm flipping the direction of the current. Get the current to flow that way instead. And same direction of magnetic field. And so now the magnetic force on the bar is going to be what direction? It's going to be that way, right? So we're taking the chemical energy stored in the battery, converting it into kinetic energy of the bar. That's a motor, okay? And you can do the same sort of thing here with a coil, which is how motors typically operate, right? We have some current that's applied, and then you can get the torque or the magnetic forces to get the coil to spin rather than try to slow it down, and you can get kinetic energy that way.